Hello everyone. In this video lecture, we are going to discuss about the chemistry of main group elements, and this lecture is third lecture in this lecture series. In the first lecture, we have discussed about the diborane and concept of the multi-sector bonding, and in the second lecture, we have discussed about the structure, bonding and important properties of the 13 group hydride, the hydride of group 13 elements. In today's lecture, we are going to discuss about the hydride of the group 14 elements. So let's start the lecture. The hydrides of group 14 elements. The group 14 is consist of carbon, then silicon, germanium, tin and lead. These are the elements of the 14 group. All the elements form covalent hydrides, but the number of compounds formed and the ease with which they are formed differ greatly from carbon to silicon to germanium, tin and lead. As we know, the carbon forms a vast variety of or a vast number of chain and ring compounds. Number 1, the very first compound are alkanes. All the carbon-carbon bond are single bond and carbon-hydrogen bonds. The general formula is CnH2n plus 2. The second class of compound is alkenes, CnH2n. And the third variety of compound or third class of compound is alkynes, CnH2n minus 2. And fourth category is aromatic compound, ring compounds. And we are not going to discuss about these compounds in the detail because we are already discussed in these compounds in the organic chemistry paper. So the carbon-carbon bond is very strong. It is one of the reasons why carbon forms such a large number of compounds with another elements like nitrogen, oxygen, etc. And since carbon-carbon bond is very strong, so the alkane and alkyne which have carbon-carbon bonds, and these compounds are formed in large amount by carbon because the carbon-carbon bond is very strong. And this is one of the reasons why carbon forms such a large number of compounds. Second, SiNH2n plus 2, that is analog of alkane. Analog of alkane, containing up to 8 silicon atoms. So catenation is also possible in case of silicon, but the value of N is not going beyond the 8, but in case of carbon, this number is large. Monosilane, that is SiH4, is the only silicon hydride of the importance. If we talk about the bond energy, the carbon-carbon bond has bond energy of 85 kilocalorie per mole. Silicon bond is 54, and germanium bond is only 40 kilocalorie per mole. Bond strength. So as we know, as we can see, the germanium bond is roughly half strong as compared to carbon-carbon bond. So the strength of element bond is decreases down the group from carbon-carbon to germanium. So carbon-carbon bond is strongest and germanium bond is the weakest. And this is the reason why we are not observing a long chain of germanium, germanium, germanium like carbon, carbon, carbon. And synthesis of selene, how we will synthesize this selene. I am not going into the synthesis of alkane, alkene or alkyne because that is the part of organic chemistry paper. So I am starting here with from selene. When magnesium is treated with silicon in the absence of air, when you heat magnesium and silicon in the ratio of 2:1, you will get magnesium silicite. Magnesium silicite, this compound. This compound is black crystalline powder like this. With structure is the unit cell structure of the unit cell is like this. It is FCC structure, face centered cubic. The corner of each corner of the unit cell and face is occupied by the silicon, and magnesium is present in the 8 tetrahedral voids. So the coordination number of magnesium is 4 and the coordination number of silicon is 8. I am not going into the structural part detail. We are just showing the structure here because this compound magnesium silicite is very important to prepare the selene. When you treat magnesium silicite with sulfuric acid, and HCl also does the same job, you can use the HCl also. So when treated with sulfuric acid, we are getting a number of selene. SiH4, it is a major product 40%. Then next member Si2H6 30%. Then next member, as the number of silicon atom increases, the percentage in the product is decreases. So the monosilane is the major product when you treat magnesium silicite with sulfuric acid or hydrochloric acid. If you want to prepare the pure monosilane, then you reduce silicon tetrachloride with the reducing agent like lithium aluminum hydride and you will get the monosilane, only the exclusive product. Similarly, you can treat the SiCl2 and SiCl3, Si3Cl8 with the some other reducing agent like lithium hydride or sodium hydride and you will get the next higher member of the selene family. So these are the certain method of preparation for the selenes. Then structure and bonding part. Let's come to this part, structure and then bonding. The structure is analogous to hydrocarbon, that is alkanes. As we know, alkane have sp3 hybridization of carbon. Similarly, in selene, the silicon atom has the sp3 hybridization. The hydrogen atom in selene are held by single covalent bond, as in case of alkane, to silicon atom, and silicon atom are held together by covalent bond. Further, this is monosilane. This structure is very similar to methane, CH4. It is a tetrahedral geometry around the silicon atom, and all the silicon hydrogen bonds are covalent in the nature. For the next higher member, if we compare this with C2H6, ethane, the structure of disilane is analogous to ethane. The hybridization is again sp3. This silicon is sp3. This is also sp3. And all these silicon hydrogen bond are covalent bond, and this silicon bond is also a covalent bond. Then properties of the selene. What are the properties? Chemical properties. How the selene behave like. The selene are much more reactive than alkanes. Point number 1. As we know, the alkane are not very much reactive, but selene are more reactive than the alkanes. The alkanes are chemically unreactive. apart from reaction with halogens and burning in air. As we know, alkanes are chemically unreactive, but they can be halogenated by chlorine, bromine, iodine or fluorine, and they burn in the air. In contrast, the silane are strong reducing agents, ignite in air and explode in Cl2. So the reaction of silane are much faster as compared to the alkanes, and they are reducing agent also. Pure silane do not react with dilute acid or pure water in silica apparatus, but they hydrolyze radially in alkaline solution or even with trace of alkali which leaches out from the glass apparatus. If you took disilane, when hydrolyzed with water in the presence of trace amount of alkali, you will get the silica, SiCO. When silane is reacted with oxygen, you will again get the silica and H2O. Similar reaction of methane with O2 is formation of carbon dioxide and water. Silane when hydrolyzed with water, you will get silicic acid H2SiO3 and hydrogen is liberated. Hydrogen atom in silane like methane can be substituted by chlorine to form SiS3Cl, SiS2Cl2, SiHCl3 and SiCl4 similar in the pattern of methane. For example, if you have CH4 react with chlorine in the presence of sunlight, there is free radical substitution and you will get CH3, Cl, CH2Cl2, CHCl3 that is chloroform and CCl4. In the similar pattern, the hydrogen atom in silane can also be replaced by the chlorine. Then what are the difference between alkane and the silane? If you look at the electronegativity value on the Pauling scale, the carbon has electronegativity of 2.5, hydrogen has 2.1 and the silicon have even less electronegativity than hydrogen, that is 1.8. Thus the bonding electron between carbon and hydrogen or silicon and hydrogen are not equally shared. The electronegative atom will pull the electron towards itself and we get the situation like this. So in case of alkane, the carbon bearing the delta negative charge because it is more electronegative than the hydrogen, its electronegativity is 2.5 and hydrogen has electronegativity of 2.1. But in case of silane, the situation is reversed. The delta plus charge is on the silicon and the delta negative charge is present on the hydrogen. The larger size of silicon make it easier to attack by the incoming nucleopile. Silicon has low energy d orbitals which may be used to form an intermediate compound and thus lower the activation energy of the process. Okay. As we know in carbon there is absence of the d orbital. So if the incoming nucleophile is coming, the fifth bond formation is quite difficult, but in case of silicon we have d orbital, so the possibility of formation of the fifth bond is more familiar as compared to carbon. Thus the activation energy is lower. So lower is the activation energy, faster is the reaction. Then come to the germanium hydrides. The germanium hydride with formula GeNH2n plus 2 and these are known as germanes. N is only up to 5. So in case of carbon, the value of N is very large, 100 or thousands, but in case of silicon, the maximum value is up to 8, but in case of germanium, the value is even less, it is up to 5. So from 8 to 5 it is further reduced because the germanium bond strength is even weaker than the silicon bond. They are straight chain compounds, they are colorless either colorless gas or volatile liquid. Similar to selanes but less volatile, less flammable, and are unaffected by water or aqueous acid or alkalis. So this is the difference between the germane and the silanes. So synthesis, how we will synthesize it? When germanium tetrachloride is reduced with lithium aluminum hydride, we will get the corresponding germane, mono germane GeH4. Second method, you can prepare the same compound from germanium oxide, germanium 4 oxide. Again the reducing agent, sodium borohydride this time, and we will get the GeH4 germane and sodium metabolite NaBO2. Then the next member of the family after germanium is tin. So stannine SnH4 is much less stable as compared to the germane and silane. The stability decreases down the group. It can be made by reducing tin tetrachloride with lithium aluminum hydride or the sodium borohydride. Either of the reducing agents work well with the tin tetrachloride. It is a strong reducing agent. As we know, this nature of reducing properties is increasing down the group. It is unaffected by water and dilute acid and alkali, but it reacts slowly with concentrated solution. Distannine SN2H6 is known and it is even less stable than the germanium analog and silicon analog. No higher stannines are known. So in case of tin, the value of N is 2 or 3 maximum. So in carbon it is hundreds, in case of silicon it is up to 8, in case of germanium it's up to 5, and in case of tin it is even less, up to 2. Then next member of the family, lead. Plumbane PbH4 is even less stable. PbH4 is even less stable and even more difficult to prepare. The preparative method used for other hydrides fail. So we cannot prepare the plumbane by using the earlier method which we are using for the lower member of the family, upper member of the family. It has been made in trace amount at low concentration by cathodic reduction. We are taking the help of electrochemistry and detect using a mass spectrometer. Mass spectrometer is a technique to detect the fragment and the ion. Then come to an exercise part in group 40 elements. Let's discuss the structure and basicity of two compounds, trimethylamine and tricylylamine. These two compounds have very similar formula. There is a nitrogen with a lone pair, and there is methyl CH3, and here SiH3, 3 molecules of each. Hydrogen, nitrogen is same. Again, these three is same. There are 3 hydrogen. There are also 3 hydrogen. Here is carbon and here is silicon. So this is the difference. But carbon and silicon are in the same family. Carbon and silicon both have the same number of valence electrons. But the structure of these two compounds are totally different and the basicity is totally different. How it is possible? The compounds trimethylamine and tricylylamine have similar formula as we can see, but have totally different structure. Yes, these are the structures. First, if you look at the trimethylamine, this compound, it has a structure similar to ammonia. It is a pyramidal structure. A tetrahedron 4 corners, but only 3 corners are occupied. One corner is occupied by the lone pair of the electron. So the shape is pyramidal. In case of trisilylamine, the structure is planar. In fact, a triangular planar geometry. This one is triangular planar. So one geometry is pyramidal with the lone pair, but the other geometry is triangular planar geometry like this. So why this structure is so different and the formula is very similar? As we know, the electronic configuration of nitrogen atom in the ground state, it is 1s2, 2s2 and 2p. The 3 unpaired electrons form bond with the CH3 group. These tetrahedral arrangement of 3 bond pair and 1 lone pair, sp3 hybridization. So the hybridization of the central atom in case of trimethylamine is sp3. And we are getting a structure like this. This is the structure. So in case of nitrogen, there are 3 unpaired electrons and 1 paired electron in the valence shell. So in the valence shell, there are total 4 orbitals and 5 electrons. So we always left with a paired electron in case of nitrogen. We cannot promote this electron here because there is no 2d. D starts from 3 principal quantum number. So there is no 2d. So we cannot promote this electron. So we always left with a pair of electrons in the valence shell of the nitrogen. So in NCS3, as we know, there is formation of 3 covalent bonds. So we require 3 half-filled orbitals. So 1 2s orbital and 3 2p orbital combine to form the 4 sp3 hybridized orbital. Out of 4 hybridized orbitals, 3 are singly occupied and 1 hybrid orbital has a pair of electrons or a lone pair. This is the case in case of trimethylamine. Let us consider the case of trisilylamine. In trisilylamine, 3 sp2 orbital are used for sigma bond. So hybridization changes from sp3 to sp2. Why? We will discuss it in a little time. So the hybridization changes from sp3 to sp2. It is sp3 in case of trimethylamine, but it is sp2 in case of trisilylamine. Are used for the sigma bonding, giving a plane triangular structure. As we know, sp2 hybridization is planar. The angle is 120 degree. The lone pair of electrons occupy a p orbital at right angle to the triangular plane. So in case of trisilylamine, we are getting sp2 hybridization. This one electron is where we can jump here to here. So it is here. And this is sp2. sp2. So every sp2 hybrid orbital, so we are getting 3 sp2. So each orbital is singly occupied and an atomic orbital 2pz or whatever be the, it has a lone pair of electrons. So in case of trimethylamine, the lone pair is present in the sp3 orbital. But in case of triethylamine, the lone pair is not present in the hybrid orbital. It is present in the atomic orbital, which is perpendicular to the 3sp2 orbital, which are at 120 degree to each other. So the sp orbital is perpendicular to the plane of the sp2 orbital. This lone pair overlap with the empty d orbital on each of the 3 silicon atoms. So this is a new thing in trimethylsilane. There is empty d orbital in case of silicon, but in case of carbon there are no empty d orbital. So the empty d orbital on each of the 3 silicon atom and result in pi bonding, and we can say this is a p pi d pi bond. P pi of nitrogen and d pi of the silicon, because it is full, to form a full p orbital to an empty d orbital. So the electron transfer from a filled 2p orbital to an empty 3d orbital of the silicon. So that if there is transfer of electron, consequently it shortens the bond length nitrogen silicon, because a double bond character come into the play. So as we know, the double bond is shorter and stronger than the single bond. So it introduces a double bond character into the nitrogen silicon bond, and consequently the bond length becomes shorter. Since the nitrogen no longer has a lone pair of electrons, the molecule has no donor properties. As we know, a compound acts as a base or Lewis base when it has a lone pair of electrons to donate. In case of trimethylamine, there is a lone pair of electrons. Here it is present, so it can donate the lone pair and it acts as a base. But in case of the triethylamine, there is no presence of the lone pair, because the lone pair present on the 2p orbital are forming a pi bond with the empty d orbital. So these lone pair are engaged with the silicon d orbital, and there is no free lone pair of electron in case of triethylamine, and it is not acts like a base. So trimethylamine is a base, but triethylamine is not a base, because the lone pair are not available in case of triethylamine. Similar p pi d pi bonding is impossible in trimethylamine, because the carbon does not possess the d orbital, and hence this molecule is pyramidal. This is the difference. In earlier I discussed, I compared the formula. There is nitrogen in the both molecules. There is 3 hydrogen on each element, and then thrice each moiety, and difference is carbon and the silicon. Both are in the same family, but there is a difference between carbon and silicon. Carbon has the d orbital, but silicon has a d orbital. So these d orbital, 3d orbital, can receive the electron density from the 2p orbital of the nitrogen and form a p pi d pi bonding like this. So this is silicon, and these are the d orbitals. These are the d orbitals on the silicon. These are the d orbitals. As we know, d orbital has 4 lobes when it is dxy, yz, zx, or x square, y square. This is nitrogen atom, and this is actually this one is pz orbital or any p orbital with 2 electron or lone pair of electrons, and this is silicon and this is silicon. The expression is like this: nitrogen form sp2, so it is planar, silicon, and there is further hydrogen 3. This is silicon. There are 3 hydrogen, silicon, and there is 3 hydrogen. So these 3 electrons are involved in this sigma covalent bonding, and a lone pair of electron is left here in this orbit. And silicon also has the d orbital, empty d orbital. This is plus, so this is also plus. This is minus, so this is minus. So the electron transfer from here to here. Similarly, the electron will transfer here. Similarly will here. So these lone pair are engaged with all the three silicon atoms. Consequently, this silicon nitrogen bond has a double bond character. There is no single bond, so it becomes short in the nature. So p pi d pi bonding in trimethylsilane we can represent like this. So the reason is why they have different structure. There is p pi d pi bonding in case of trimethylsilanamine, but there is no p pi d pi bonding in case of the trimethylamine. Thanks for watching this video.